This session is called Spark in Theory and in Practice, and I think what is interesting is my perspective is from not a data science perspective, not a statistics perspective, but I guess from a hacker perspective. I have a little bit of a background that I think has lent itself well to the type of data science tasks that we want to do. So, my background is, I studied computer science at Chalmers University. I did formal logic and algorithm design. And so while I was at Chalmers, instead of doing my courses dutifully, I was a hacker for the Dragonfly BSD kernel. And the neat thing about that was, I guess I became very good at assembler and C, and I developed a little bit of a silly disdain for high-level languages like Java and which was difficult because a lot of courses were in Java, so we had to learn them. But and also JavaScript, which was sort of a sissy language back then, but I guess now everybody else is laughing at me. So so now JavaScript is pretty performant. But the interesting thing about working with operating systems was that it was sort of a bubble of sorts, because the types of problems you tried to solve in operating systems were a general type. So you have processes that are running in an operating system. You don't know if they're good, you don't know if they're evil, you don't know how much CPU they require. They do input-output. You know, it's a multi-tenant environment. It's essentially these big data platforms that we're doing now, except on one machine. And then also, when I was starting in the early 2000s, multi-core was a big thing. So everybody was trying to figure out what the best strategy was for scheduling things on multi-core processors. And yes, functional languages was also a big thing at Chalmers, that they thought we're going to leave everything behind and you're just going to express things like as if it were a mathematical equation, and you know, the compiler is going to figure out underneath how to do everything. We're there a little bit right now with Spark and these other big data applications, but I think understanding these things can make you make better decisions when you're implementing big data systems. Understanding how scheduling works, understanding, you know, priority inversion when you schedule stuff, understanding memory alignment and all that kind of thing. Even if you don't have to do it, understanding it lets you make more clever decisions. And more importantly, reason about whether a certain result is realistic or not. Is it really realistic to import this amount of data on this amount of nodes and expect this type of response before you spend 3 weeks? Yeah, that wasn't a good idea. So, let's get going. What is big data? So big data right now is trying to solve the issue of out-of-core computation, meaning computation that doesn't fit in memory, computation that is distributed over many machines because it doesn't fit in memory, but then it still doesn't fit in memory in the distributed machines, and then also doing general purpose computation. So obviously if you know the computation beforehand, it's not very easy, but you can over-optimize. These big data platforms are supposed to solve general purpose problems. And in my experience in operating systems, parallelizing stuff in general is very difficult. From physics, there are good examples. If you take a bar of steel and you try to bend it, you can't split up that problem, cutting it in half, and only figure out the tension on the bar of steel on the left side and on the right side, because it propagates from this one to that one. So there's no trivial way of splitting it up. The same thing with crack propagation. If you were to hit a rock, the crack propagates in a way that's not easily parallelized. And so one of the things that makes parallelization very difficult in computers is input-output, which is why locking certain resources so that when one reader reads and then wants to do something on that data, another actor doesn't come and change it while the first reader is doing something. That's what databases are so good at, and why, generally speaking, it's very difficult to parallelize databases, because if you have one person doing a withdrawal on a bank account on a node over there, rewriting the balance of a certain cell, and then another person tries to do a withdrawal at the same time, if the layer isn't cache coherent, meaning all the nodes see the exact same data at the exact same time all the time, both people are going to pull out the money at the same time, even though there's not enough of it. So these types of problems are very difficult to parallelize, and there is no framework that solves them. So Spark doesn't automatically parallelize everything magically. The solution that Spark, MapReduce, and all these other things do is take advantage of data parallelism, which means it doesn't actually solve anything at all. So I'm just going to be a bit cynical here, but you'll understand why these things are super useful anyway. I remember when MapReduce first came out in 2004, people were saying it was amazing and Google was super duper awesome, as always. And when I first read the algorithm, I didn't get it, because I was like, what is it you're solving here? This is the example that Google used the first time. It's important to understand the history, that's why I'm going to go through it a little bit. Google used word count as their first example of how MapReduce is so good, and it's relevant for them because what they wanted to do was go through web server logs and count page hits, count links between pages and that kind of stuff. And so if you imagine a big document, the Bible, and you want to count how many times the word Lord appears in it and that kind of stuff, you could split it in half, ask one person to count the times that Lord is in the first half in the New Testament, and another person that counts Lord in the Old Testament, and then they just come together. It's like, I found 400, yeah, 300, okay, that's 700 total. That's easy to parallelize, and you can get, the more people you get, you can parallelize it easy. That's because the data is not interdependent. The number of words you count in the New Testament doesn't affect ever, no matter how you choose to count it, from front to back, back to front, in parallel and that kind of stuff. It doesn't affect how many words are counted in the other half. So MapReduce works in the following way. This is not the entire code, but in pseudocode. The first part you see, you give Map a document, the Bible, and the contents of it, all the words inside the Bible. And what it does is, for every word, it creates, and it can do this in nodes. So if you have 10 nodes, it'll split it in 10 different pieces. And that's sort of the neat part, that you don't have to do this splitting and sending and getting back and forth again. But it'll count the words independently on each node. And then, once it's counted that, it'll send it to another node or keep it on the same node. And it'll put those together and send them all back to one node and count them together. That's it. That's essentially MapReduce. Now, you can take a number of algorithms, SQL queries, or whatever, and translate them into this graph of computation. And that's what Hive has done. So you can type a SQL query, and it'll translate it into precisely these steps. This is pretty neat, but it is a bit limited in the types of computations that you can do. So for the first thing is, you have one input and you have one output. So if you want to do something more clever, like, actually I want this node to recalculate what it's done depending on what the answer is from the other node, you can't really express that without letting it all go through to the end and then sending it back to the beginning and doing this whole thing again. And the way MapReduce was written from the beginning was it would flush things to disk because the data sets were so big. But it was a little bit inflexible in that regard, and the database people made fun of MapReduce a lot in the beginning and said, well, we've been doing more advanced stuff for a long time. But one of the neat things that MapReduce did, or that this set of tools did, was solve picking up data off the disk one piece by one piece, so you can do out of core. It solved a lineage problem where if one node would die, this graph is simple enough that it could just pick up where it left off and move forward, and a number of other things. It relied on Google's distributed file system, and so one of the big important principles in MapReduce was that rather than do the computation on each node and send things around, the scheduler that would send out the code to each node would send it to the node where the data was, so you wouldn't have to send data across the cluster. So that was a pretty clever invention. But in a year or two, Microsoft came up with a neat upgrade called Dryad. Not an upgrade, it was their own product. And it was built, inspired by databases, general purpose GPUs that started to become popular in the scientific community, and MapReduce. But what was neat here was that they sort of skipped the MapReduce paradigm and thought of things in terms of a directed acyclic graph. In other words, a graph of computation that doesn't contain circles in it. And they actually gave these as examples where you would have, a text file that would be split up into 3 pieces, sent to grep, 2 of them would be sent to another sed, that kind of thing. And you can see here that you can express a graph that's a bit more sophisticated than MapReduce. What this didn't take into account was data locality and a number of other things, but the types of algorithms you could express were way more advanced. So Microsoft came up with a language called Link Dryad, or Dryad Link, that let you type SQL queries, sort, and all that kind of thing. And this is sort of where the functional aspect that we see in Spark now came from, where rather than programming your code in terms of a map step and a reduce step, you would have a function called sort or something like that. And Dryad underneath would turn that sort function into a little network of instructions that would execute it, sometimes in turn, sometimes they would wait for each other and that kind of thing. And you could express pretty sophisticated computations this way. In specific, machine learning, which requires something called backpropagation, so that you do the same step over several times. But then finally came Spark, and Spark has an interesting background in that it wasn't invented for its own sake. And I'll get to that in just a second, but if we just talk about what the original Spark paper talks about, the central idea is the resilient data set. So the resilient data set is an abstract data type that can be anything. It could be a graph, it can be a nested data structure, it could be a table, or it could be binary data or anything really. And it's designed to read from a distributed storage. And the principle behind an RDD is that it's immutable. And again, this comes back to the path of least resistance type thing. If a piece of data never changes, it's not really difficult to orchestrate things between nodes, because one node will never overwrite the data. One node will never see something that another node does not. So it really simplifies things. And one of the first examples they gave was machine learning and interactive analytics. So here at the bottom, I've written something called a REPL, the read, evaluate, print loop, I think it stands for, which is that you can type commands and get answers immediately. That was one of the first things that the Spark people came up with, because when the data is in memory and it never changes, you can create a graph of computations on it and say this is how it should change. But instead of moving the data and changing it, you just remember what the instructions were backwards. So you can make a big graph of computations on it, and you only have one copy of the data in the beginning, and it'll transform all the way down to the bottom. And the advantage of this is if one node dies over here, you have a lineage, you can go backwards and say, oh, I can rebuild this data again if I just go back 2 steps and take from there and move forward. So, I removed a couple of points here, but the nice thing then is that Spark keeps it in memory and lets you do new things over and over and over. And it was built using Scala language, which is a functional language that works on the JVM, on the Java virtual machine, so it's quite high level. You don't know how many compute cycles anything will take. It's a bit of magic, but you just have to accept that. And nowadays, everything is pretty fast, because computers are pretty fast, I guess. But the idea is that rather than iterating over things like you used to do in MapReduce, you would provide a function that, you would use a function that Spark provides, such as apply to every element in this data set, or sort every element in this data set, and you would sort of chain these functions to each other rather than programming explicitly what you wanted to do. And Spark would handle the building of this graph of execution in the background. And now in Spark 2.0, it's become super sophisticated, and I'll get a little bit into that in just a moment. But if we compare the MapReduce code to the Spark code, so this is how you would scan a log file to see if there are errors in it. You would read in a file from HDFS, you would create a function, or not create a function, you would create a variable called errors with the help of a function built into Spark called filter that looks for the word error. When you do this, it doesn't actually do anything in Spark. It's not until you call the row after it to map, no, actually, this is also an instruction that says for every entry that contains the word error, create an extra column with the number 1 in it. But still, Spark hasn't done anything, because what you're doing now is you're building a little graph in the background of computations required in order to execute this. So it's not until you actually write ones.reduce and count and actually ask for the answer back from Spark that it'll start executing this graph that it's created. And then if you want to, you can cache certain things in memory so that if you want to take the errors and do something else with it later, you can do that as well. So we've moved very much from this iterative programming paradigm to a functional programming paradigm. But one interesting tidbit is why Spark was created, and that was there were a bunch of people doing scientific computing in a data center, and they needed to share resources with each other. And it's very difficult to schedule resources on computers, so there's this framework called Mesos, which uses a preemptive two-layer scheduling algorithm, meaning it doesn't assume that the processes running on your cluster are nice or ever release their resources. The equivalent in Hadoop now is Yarn, and you can run Spark on Yarn, but this is a bit more of a flexible framework that allows you to have multiple cluster things living next to each other that have different scheduling policies and that kind of thing. So the team at the AMP Lab created Mesos, and then they needed an app to prove that it was good at scheduling stuff on many, many nodes. And so they wrote Spark in order to prove that you can run computation next to NPI and some other algorithms that existed then. So Mesos came first, and Spark was just a fun idea that turned out to be really good, actually. There's one other thing that's worth mentioning that I think is a really neat program. Is called Aluxio. It used to be called Tachyon, and it's the follow-up to HDFS. So Aluxio uses the same principle as Spark of this lineage graph where you change things as little as possible and then rather store how things mutate over time. And it does that in memory, so when you write something onto Aluxio, it doesn't actually necessarily write to disk. It writes to memory the changes and then slowly after time flushes them to disk. So companies like Baidu and other are accelerating their Spark and Hadoop jobs by having Aluxio live on top of HDFS, and it just looks like HDFS in memory a little bit, but it can accelerate their computation by 100 times. So Mesos and Aluxio sort of came out of that same AMP Lab place. But if we look at what Spark is today and what it can provide, Spark Core is a little bit what that first paper was talking about. Spark Core provides out-of-core distributed processing. And why that's important is everybody always laughs when a person that programs R tries to load a data frame that's 20 gigs on their poor laptop and then it dies like that. Spark also provides scheduling, meaning if something goes slow on one node or you're doing multi-tenancy, it handles all of that nicely for you. It does I/O. It can do parallel I/O. It can do clever things. That's always a pain to do on your own. And then finally, the neat thing in Spark 2.0 is it generates code, sort of like a mini compiler. So instead of asking certain functions to run, it'll actually write code in the background instead of doing lots of function calls and that kind of stuff. Sort of like databases do when you do a gigantic query, it'll generate programming code and run that instead of calling all of the functions sequentially. And this really speeds things up. We will see exactly why Spark can spank a C++ program even though it's inherently much slower. I'll give a little demo of that in just a short sec. The next feature of Spark is the SQL feature. And I think this is a little bit why people like Spark so much, which is it's such a multi-tool and it's good enough at everything that it's too much of a pain in the butt to use the best tool for everything all the time, that it's simpler to spin up Spark and use the functions that are built in. So Spark has really good SQL support. In fact, it can run all of 99 TCS DS queries unmodified, and in fact beats a lot of the big databases like Teradata and Oracle in many cases. It reads data, again, in I/O, so you don't have to deserialize stuff yourself. Avro, Parquet, or C from Hortonworks, JSON, you name it. And then finally, you can treat it as if it were a database by connecting to it with your favorite tool, Power BI or whatever, via ODBC. Spark Streaming was sort of, all of these came afterwards as add-ons, some from the AMP Lab and some from contributors. But Spark Streaming, again, with the I/O, I think one thing that's important to remember when you're working with open source tools in general, or proprietary tools for that matter, a proprietary vendor will be like, we have streaming support. Yeah, but the fact is you sort of have to have that tool in an ecosystem. It's not going to live on its own unless you buy everything from that vendor, and then it turns out they don't have the features you want anyway. So you grab their streaming stuff, you put it in the middle, and you're like, okay, I'm using 0MQ, or I'm using Kafka. How do I ingest from that? You have to write your own consumer and producer and start doing this, and we have the proprietary language. Okay, Spark is already integrated nicely with Kafka, Flume, Twitter 0MQ, and can take TCP streams, traps, any other types of network binary data that flows around. Kinesis also, if you're a fan of AWS. So that's very nice. But it doesn't handle things on a one-by-one basis like a true streaming solution, because it wasn't designed that way to begin with. It just takes the tables and make them a lot smaller. So you decide how long you want your time window to be, and it'll slide along. And there is an issue. If you want the time window to be less than 10 seconds, it's going to have to start spinning up lots of jobs in the background, which is why other streaming tools like Storm or Flink are much faster and can get sub-second latency when it comes to streaming stuff, because they handle one event at a time, whereas Spark handles little frames at a time. But there is a new feature called structured streaming, which I will get to, that makes this still a very compelling streaming platform, and one that I think is very important. But before we get to that, let's just go through the last features. MLlib, I remember when it came out, it was called nlib to begin with, and it came with all of the popular functions, PCA, and it can export to PMML. It has a nice way of making pipelines so that you can train your models, send the stuff back, train the model again, score, do that kind of stuff. It's all built in again with this multi-tool type thing. Although, when it came out, it was already pretty popular to be using deep learning, latent shit, and other algorithms. Not sure how that name is pronounced. And I was surprised that none of them were implemented, and it's probably because they're very difficult to implement using the directed acyclic graph method that Spark uses. For instance, a recurrent neural network is very, very difficult to implement in the back end of Spark, which is probably the reason why it hasn't shown up yet. And then finally, Spark has something, the last feature that was added to it was GraphX, where it can, you can use either the Pragal abstraction, which is a way of talking about graphs, or you can speak in terms of vertexes and edges. So it handles both of those. What is Spark really? For me, as a hacker, it's just an API that I can access from one of my favorite languages, and none of them are listed here. But Scala and Java are the two big ones, and I listed them in this order in specific because this is the order in which you want to use Spark. R is the one of these that I'm most familiar with, and it's the worst one. It doesn't support, it doesn't support GraphX, it doesn't support a bunch of other stuff. Scala supports everything. Not only does it support everything, but expressing these functions in Scala looks really nice because the functions were written to be expressed functionally and not in an object-oriented way like in Python. So if you want to do some mathy type transformations in Scala, you actually write the math formula, whereas in Python you would have to call the function pow and then embed the number in there, and then it looks really bad object-oriented. I said this is what Spark is the bottom ones. Spark is changing really fast. 54 APIs were deprecated in Spark 2.0. And experimental APIs are coming up. So there are a lot of APIs to choose from, but not all are equally stable. And if you look at some of the Hadoop distributions like Cloudera and the other ones, they will offer support for large parts of Spark, but not everything, like GraphX. You can either go with their recommendations or you can test your way forward, but don't assume that just because it's part of the product that it's necessarily equally stable as anything else. Lastly, this is something that's super boring and not really part of the plan, at least in Spark, but in the Hadoop distributions, they have ways of doing data lineage. And by data lineage, I mean, who did this query, where did the data come from, and that kind of stuff. So Cloudera and the other ones, they have plans on how to implement that on top of Spark eventually. What is Spark from the public's perception? So Databricks, the company that was founded by Matej Zaharia to promote Spark and sell Spark and support Spark, did a nice questionnaire. I think it was over 1,000 people that answered. Very nice representation from a bunch of industries. This is what people think Spark is. Spark is the fastest. Spark is also the best for advanced analytics, super advanced analytics. Spark is also very easy to develop for. and very easy to deploy. And also it supports streaming, and streaming is hot because that's like IoT and stuff. So I'm gonna go through these backwards because I like the top one the most, and that's the one I have the most experience with, and also advanced analytics. But if we go back for a second to streaming, the bottom one there, I mentioned before that Spark has something called structured streaming now, which is, you know, when you're getting in data and you're splitting it, this is, again, the data parallelism problem. That's the real problem that sort of people ignore. If you're counting something like web logs and you're counting sessions started and sessions stopped, you're doing it on a static data set, you will get an equal number, hopefully, unless your web server's sort of messed up. You will get, you know, the people start their session, they end their session, and they're equal. If you're doing that type of counting on a streaming data set, one node might complete before the other node, and all of a sudden you have more sessions closed than started, and then that becomes part of your input pipeline to something else. So you do have an issue when you're talking about real time, in specific, something called concurrent processing. So the difference between parallelism and concurrency is that concurrency means that the order is not necessarily defined ahead of time, whereas parallelism means that you run things at the same time. So when order makes a difference, for example, open and close session, you need to keep track of those two things, and Spark structured streaming can do that. But as you can see, and also it has exactly once support, which these other ones don't necessarily have. But Apache Flink does have support for doing one row at a time, and Spark is still going to be doing little batches at a time. So if you need sub-second latency, might not be the best tool. The next thing is ease of deployment, which I absolutely don't agree with. But if you've already installed Cloudera, it comes as part of it, or Hortonworks or whatever, so I guess that's ease of deployment, although setting up those systems isn't trivial either. But Microsoft Azure has a really neat service called, I think it's called the container service, that makes use of something called DCOS, which is the Mesos scheduler that I was talking about before, together with a cron-like software that lets you say what times you want to run things in. And Mesos uses, instead of processes as an abstraction, uses Linux containers as an abstraction. So you can run anything on this. You can run your chess software, you know, to calculate what moves you should be doing in chess, and you can also run Spark, or you can run your Perl scripts and that kind of thing. And DCOS has these easy peasy deploy things. You can click Spark and it'll deploy Spark to your cluster in a couple of minutes because it uses containers. So it's super duper handy, and this is, in my opinion, is the easiest and best way to deploy Spark, unless you're going to install Hadoop everywhere. And even so, if you want to try out other neat things like Kafka or Flink or whatever, this one's got you covered as well. So DCOS is something I would recommend for you guys to look into. What was the middle one? I think I forgot one in the middle, which was ease of programming. Yeah, I guess you guys will see that. All right, it's demo time, baby. Enough, let's see. Okay, half, that's good. I have half the time left. Okay, so I have remoted into our network. I guess I forgot to say what I worked with. I worked at Microsoft for a long time, Tele2, and now I'm the CTO of my own big data company. So that's fun. Let's see if this is going. Everything looks good, and that looks good. Okay. So we have a couple of machines that are ours here, and I was going to go through a notebook with some example Spark stuff, and then show a little bit some of these principles, how they work out in practice. Let's run all of this. Oh, you can't see anything. Let's do like this. Project, duplicate. And now this text might be teeny tiny, so I think maybe I can, no, not zoom in like that. Let's see. Plus. How do I zoom in? Yeah, maybe. Is that okay? You guys? No, that's horrible. That's really bad. Let me try to zoom in just a bit more, and then that's really bad. Maybe I can do like this, and then you guys can see if I want to zoom in. Okay, so first command, load all the libraries. So I'm programming from R, the worst language, because I want to show the least common denominator. This is actually, okay, I already started it. I just cleared the cells. Does everybody know what a notebook is? Everybody knows. Everybody's not going to be awesome. You guys that don't know it. Okay. So I'm running a notebook here with R, and this is a neat package that Cloudera and I think it was R, what's it called? That RIDE, R Studio made together. And they let you interface with Spark much more nicely than the native API that Spark released. So this one, I started Spark Context, and what it gives me is a set of tools that are similar to Deploy, if you know that tool in R. And this one lets you do sort of the same thing. So if we look at the iris data set, is a very famous data set of little flowers, and load that into a Spark RDD or a Spark data frame. We have the iris table. Okay, let's zoom in actually. We have the iris data set here in R, and we can just Spark copy it into a Spark data table. That went pretty fast, but it's also a very teeny tiny data set. If we look at what type of data set the original R data set is, it's just a little list of stuff. Let's take a look and see what it looks like. Yeah, it's a little table, the length of the petals and the width of the petals. Okay, so we keep going. If we look at what the data frame in Spark is, it's also list. However, it is not the same. So here, it'll tell us if we list the table that we moved into Spark. It's one of the Spark connections. We're connected to it, and we queried it using Sparkler, and all the values are in there as expected. So let's look at flights data. I think is pretty neat. This is going to be an example of interacting with Spark, wherein it keeps the data in memory. So we've loaded the flights data. This is a bunch of flights from New York in 2013, also part of standard R. We copy it into a Spark data frame. We can look what tables are available to us. I guess I've created a table called A, and flights, and iris there. And what we do is, the first step is, sorry, this is really small. Maybe it's not super important that you know, read exactly all the code. It's the principles that are more interesting. We'll filter the departures by delay. Okay, that was pretty quick. Interesting. Let's do another bit of filtering here. This filtering here was, let's see. Yes, this arranges the data in a neat way. This is something I got from the New York flight data set. But it arranges it in a way so that you can see the delays per airplane, per airport. So we're using functions that are built into Spark here and chaining them after each other. For example, group by, summarize, mean, filter by ones where, where count is over 20 and distance is less than 200, and chaining them after each other. And let's run that. Did we run it? Yes, we ran it. And then we can use the output that's returned back to R. So the computation is done in Spark, and then the result, which is much smaller than the data set itself, is returned to R, and we can plot it out and see a nice little plot. And we can use this type of interactive way of working with Spark, where you have the gigantic CDRs from the telco or whatever, and they're being chugged in Spark, and then you just pull out, you know, a couple of thousand rows and plot it, or save it to a CSV or whatever. So that's a pretty neat way of working with it with regards to interactivity. And Sparkler in particular uses something called a DPI interface, which is an R-specific way of expressing SQL queries. So we can send that SQL query, select from, so forth, to the Spark context that Sparkler is holding onto, and we'll get back a nice little table. So you don't only have to use these functional, expressive ways of talking. You can use good old SQL if you want to. Unfortunately, the Sparkler API is not quite as full-featured as all the other ones. But this is something I like. Okay, computation. Let's do something more fun. Let's create a normal distributed random array filled with lots of numbers. So yes, and copy it to Spark. Unfortunately, I wanted to use a matrix that was 10,000, but the JVM dies, so I couldn't do that. And that's Spark's fault. So what I want to do now is I've created this big array, and I'm going to do an element-wise product multiplication. It's not so important what that is, but the point is I'm going to iterate it over a bunch of times just to set one processor working a lot, and I want to profile it a little bit. So let's see here. I'm going to bring up, this is some of my old OS stuff. Let's do it like this. Let's check what process it is. I also figured out when you copy stuff from R to Spark, it's single-threaded, so it goes super slow. That's why I also didn't want to use the gigantic matrix. Okay, so the process is, let's freeze that. Okay, the Spark process is 11.639. We're going to run a little bit of, I guess you can say debugging if you want to. 11.639. I'll explain it just for a moment. There's too many things at the same time. 629, I said, right? Already forgot. There. So what I want to do, 11.6, oh, it was 39. Okay, what I want to do now is use the perf tool that's built into Linux. So perf uses counters in the Linux kernel to see what's going on the CPU. And you usually use this to debug your C++ programs and that kind of thing to see what levels of cache it's hitting and that kind of stuff. So let's just run the Spark computation here, and this should take about 50 seconds. So I have a little window. I didn't want to do a bigger computation. Let's see, like that. Let it run a little bit hot. We'll start the perf counter, and it should return in just a sec, in 5 seconds actually. And why is it not running? I'm running over my phone now, so if there's a little lag, it's because of that. Oh, it's not running. Now. 4, 3, 2, 1. Boom. Okay. Okay, well, we messed up. It went too fast. Let's try it one more time. Boom, now the cache is hot, so it's going to be even worse. Let's do it one more time. 3, 4, 5. Okay, excellent. CPU is fully utilized, 100. And what we see here is 16% 16% misses on the lowest level cache, the big cache that the processor has. Why is this interesting? Well, let me compare to my favorite language, Julia. So here's Julia. Julia is a super awesome language that all the neat hackers know, and it's good because it's like Python in that it's easy to use. It's expressive. It looks like MATLAB. You can, actually, let's do it like this. You can, okay, I'm not going to talk too much about Julia, but you can, you know, let's see if we can get my keyboard to work here. You can use UTF-8. You can use UTF-8 in your program, so you can actually program with physics constants and that kind of stuff in the program. You can use the UTF-8 symbol for a union between sets instead of X in this set, and that kind of, it's the best language. But you guys, that's a separate presentation. In any case, let's see here. Is that dirt on my screen or a little hyphen that jumped in? There we go. I will create a little tool with a little matrix with a tool called Dagger, and Dagger is similar to Dask for Python. It's an out-of-core computation framework. And what I did here was I created the same matrix that I created in Spark, 1,000 times 1,000. I wanted to create the 10,000 one, but that wasn't possible in Spark. But I created 1,000 times 1,000 matrix, and then split it up into little 70 by 70 matrices, and then let Dask sort of send them out over the processors and compute stuff in parallel. So let's see, we created the array, and here it's also lazy, so it hasn't actually done anything until I call compute. And there, it computed it. That was pretty fast, the random matrix. And then we gather it. You can take a look, lots of random numbers. Sweet. What I want to do here is run 1,000 iterations of a square sum over this matrix. That'll take about 60 seconds because I've tried it before. And I'm going to run the same perf test on it. So let's do that. 1, 2. Run that. Julia should jump to the top. And he said, oops, I don't want this. Julia 11978. 11, come on. 11. 978. Go. And let's see, hopefully this hasn't finished yet, yes. What I'm trying to get done here is show, I know for a fact that when this is written correctly, it's 100 times faster, because I've done it before. But in this case, when I'm just using it as is, it will run very slow. And the reason why, you will see here in just a sec, if this thing ever finishes. This is a very long 5 seconds. Still going. There we go. Oh wow, look at that. 50% cache misses. So it has to go to the translation look-aside buffer, find where in the virtual memory it is, go to the main memory. An L3 cache miss will take 1,000 clock cycles to get the data out of memory, whereas getting it from the L3 cache will take about 30 instruction cycles. So that's a difference of 300 in performance. And that is because the data structures were not memory aligned here. I cut them up into those 70 pieces. Spark does that automatically. So that's what the power of Spark is. Spark is not the fastest, but Spark is a really damn useful tool when you don't care about stuff. And I will get to the last part here, which is my favorite, the machine learning part. And let's go to machine learning. Okay. Again, I'll simply say what's on the screen here, and you'll have to trust me. We will copy a little data set called empty cars. It's a silly data set of cars and how many cylinders they have, how big they are, and that kind of thing. If we look at it, let's take a look here. You can see it says miles per gallon, how many cylinders, how many gears, that kind of thing. So we have this little table here, and we pull out all the rows that have horsepower of 100, and then split it into a test and a training partition. Okay, the zooming thing's not working. A training and a test partition. Let's do that. That'll go pretty fast in Spark as well. Excellent. Let's do a linear regression on it with the miles per gallon as the response column and the weight and the cylinders as the input column. So it should be able to predict, given the weight and the cylinders, what the mile per gallon is for this car. That was pretty fast, maybe. But if we look at the response here, how good is the model that Spark has created? Root mean squared and R squared, 86. Good, it looks like it's pretty good at predicting the miles per gallon based on the cylinders and weight of the car. But there's a much cooler tool that I like called H2O that works very well together with Spark, and this is what I recommend you guys to use, because for the really heavy lifting, there are a number of tools that you have to use, because if you want to define your own networks, your own activation functions per layer, you want to do little magic things, you can't both have super simple to use interfaces and all that power at the same time. So H2O is for doing deep learning and all of the new algorithms without having to care about normalizing all your columns to one, turning all your strings into one hot encoded cells, doing all of the dirty work. And I'll show you exactly how easy it is. But the first thing I wanted to show is that H2O integrates with Spark because it's written in Java. No, not because it's written in Java, but it does integrate very nicely. It lives in the same process. And I didn't show you before. Now it's training using, no, we're moving it from Spark into H2O. What I didn't show before was when I wanted to make that 10,000 size matrix and move it into Spark, I told you that R is single-threaded when it moves stuff from R to Spark. It took like an hour to move that stupid frame from R into Spark. And if you have something that lives in the same operating system process, they share the same memory. So this should go pretty fast in theory. And this went faster than the R example, so that was good. I guess that is proof. And then we can call H2O programmatically here, linear regression as well. And you'll see that the fit is pretty much as good. But I want to show you a little bit what H2O really is, because it has a nice interface that sort of gives you a better feeling for why you would want to tack H2O on top of Spark, and why Spark for advanced analytics isn't really where it's at. I know a lot of people are doing advanced analytics now, and we're doing machine learning because we have a decision tree. Random forest, the most advanced decision tree, was invented like in the late 90s. So it was cool then, and then finally SAS got it into their products, a couple of years ago. So that's good for them. But the rest of the world has moved on, and there's lots of other algorithms that are very neat that you want to have, because the difference between the algorithms is so great. If you can lift your accuracy from 92% to 98, that's essentially, that's like an ocean. That's the difference between how good a dog understands Swedish and a human understands Swedish. It's a couple percent points, but the difficulty is huge. So I don't know why this training is taking so long. I'm going to interrupt it and show you the interface instead, because it's very nice. Let's go ahead here. If we interrupt, doesn't want to interrupt, doesn't matter. We'll start it manually. H2O. And H2O. Go. All right, let's see. Where does it, and it's already running. Excellent. So H2O comes with a little notebook built in that makes it easy for you to get started with it, and then once you know how it works, you can go back and control it programmatically like I was doing from the Blur. Let's just go and look at one example then. Let's see, where are the examples? Here is a neat one. I want to show the MNIST data set. The reason why I use MNIST, and people, where is MNIST? Deep Learning MNIST. The reason I use MNIST, how many people here know what the MNIST data set is? Okay, the MNIST data set is handwritten numbers by poor university students, 70,000 handwritten numbers, and the task is to classify, looking at the picture, what's the number in the picture. So they're pretty small. I think it's 23 by 23 pixels. And the reason this is a neat problem is 23 by 23 pixels is actually 700 variables. Why is deep learning really good at this compared to random forest and that kind of stuff? Well, because the relationship between the pixels is nonlinear in several stages. There's no way to look at any individual pixel and say, when these two are on, it's definitely a 7. It's the contiguous line that goes over a certain region, which is a high-level feature that you have to be looking for, not specific pixel stuff. So if you train a random forest on the MNIST dataset, it will never get better than a 5% error rate, no matter how many hours you let it run. If you let actually I'm not going to run this code because I'm running out of time, but if you let deep learning take a look at it, it will get down to 1% in a couple of minutes error rate. And if you let it run for a couple of days, it'll get down lower and lower and lower, slowly, linearly. What's really neat about H2O on top of Spark is that it lets you take advantage of all of these deep learning advancements, the other types of dimensionality reduction advancements, autoencoders and that kind of stuff. So you can do your data preparation in Spark, move it into H2O, and move it back out. And H2O will let you create a POJO file, regular old Java file, and you can load that into your code and score stuff. It's all part of the same ecosystem that I was talking about before, being like a good data citizen and having everything in one place. But I want to show you, I actually wanted to demo this machine, but it's a little bit busy, this one machine we have. We're doing some image classification. Actually, I can show that. It's training. We have 4 GPUs in it, and it's climbing very, very slowly here, going upwards at 33% accuracy right now over the complete data set. And they're very hot, so I'm always taking a look and seeing if this machine is doing well. But I have one example of the MNIST data set that I've done here. So this machine has 4 GPUs. Let's see, models. Yes. This machine has 4 GPUs, and if I run the deep training on 4 GPUs, it actually goes slower because it's too fast on the 4 GPUs. So I'll just explain what this picture here is. This is me training on the MNIST data set, which on the CPU would take maybe 10 minutes to get to 1% accuracy. With random forest, it would take a couple of hours to get to under 5, maybe 4.7, something like that. If we do a mouse over here, we should be able to see. Oh no, it's because I've zoomed in. Let's do a mouse over and check if you guys can see. No, you can't see. I'll just read it for you. The accuracy is 98.9, so it's down to 1%, and it took, how long did it take? It took 8 seconds, of which a couple of seconds were the startup for the process. So what would you do if all of a sudden your training, your scoring, and all of that kind of stuff could be accelerated with GPUs so that you can get answers in a couple of seconds? In this case, I wouldn't be using Spark. But the point is that you sort of have to understand the domain and the problem in order to make good decisions. That's a little bit what I had to say. Let's see, I have a nice slide here. This is our little GPU machine that we run all that stuff on, and it makes the room super hot. Also, you guys can get all these slides. These are probably what I would consider the state-of-the-art machine learning tools. I think you were speaking about TensorFlow before. I came in just a minute. Tensor, it's a bit silly because Tensor is always a 3-dimensional construct, and no machine learning uses that nowadays, but it does sound cool. Also, I'm a bit Google skeptic. In any case, what is Spark for? What is Spark really for? Spark is for out-of-core computation. Can you fit it on a GPU? Probably shouldn't run it on Spark. Can you load it into memory? Maybe. If you don't have time to do things the right way, it can be really neat to load it into Spark and do something quickly. Are you going to build a product? Probably not a good idea to do it in Spark because you can't close the source code and distribute it. What else does Spark do? It has everything in one place. You don't have to put it into a database in order to write a SQL query. You don't have to put it you don't have to transform the data to do a graph query on your table. Fault tolerance. That job that I showed you before that's running on the GPU machine that's scanning 10 million pictures. It's a couple of terabytes of images. It's going to be running for another 2 weeks. It's a real pain in the butt if it messes up in the middle. Spark is that kind of thing also. If you're going to do a big batch job, it takes care of all of the fault tolerance, checkpointing, going back in time and rebuilding things and that kind of thing. And then finally, scheduling. Spark is part of a big data platform. It's going to live together with other things, and that's why if you're going to be writing things manually in Python or anything else, you're going to have to take into consideration how does your code play well with the other applications. That was all I had to say about Spark. Thank you very much.